In the year 128, Emperor Hadrian dedicated a domed building in central Rome that had no rebar inside it, no steel, no modern reinforcement of any kind. The dome was 43 meters across, the largest reinforced concrete dome ever built in human history. It still stands. Tourists walk under it every day. Roman aqueducts built with that same concrete still carry water into the city. The harbor breakwaters at Pozzuoli, poured into the Mediterranean before the birth of Christ, are still intact under the salt water 2,000 years later. The parking garage at your local mall was built in the 1980s. It is crumbling. The Fern Hollow Bridge in Pittsburgh, 50 years old, collapsed in January 2022. The American Society of Civil Engineers, in their 2025 Infrastructure Report Card, classified over 46,000 bridges across the United States as structurally deficient. Roughly 42% of every bridge in the country is over 50 years old. The average design life of modern concrete is also about 50 years. Do the math. How did we go backwards? That is not a rhetorical question. In January 2023, a team led by Professor Admir Masic at the Massachusetts Institute of Technology answered it. And the answer connects directly to a piece of chemistry so cheap and so simple that it has been sitting in industrial catalogs for over 200 years, and which, used carefully, can dust-proof your garage floor and seal the hairline cracks in your driveway this weekend for somewhere around $15. I want to be honest about what this technique can and cannot do, because there is a small industry of videos online promising it permanently fixes every concrete crack on Earth. It does not. But within its actual capabilities, this is one of the most underpublicized methods in home concrete maintenance, and the markup between the raw industrial chemistry and the branded version at your hardware store is somewhere between 10 and 50 times. Here is how it works. Where it works, where it does not, and why no one ever taught you about it in your hardware aisle. Start with the Pantheon, Hadrian's dome. The Romans did not have steel rebar. They did not have modern engineering software. They had three things: volcanic ash from the Bay of Naples, quicklime, and a technique called hot mixing, where they combined the lime and ash and water all at once, generating a violent exothermic reaction that hit very high temperatures inside the mix. For 2,000 years, historians and engineers assumed the secret of Roman durability was simply the volcanic ash. The ash is a real factor, but it is not the whole story. The MIT and Harvard team published their finding in the journal Science Advances on January 6, 2023. They had taken Roman concrete samples from the wall of the ancient town of Privernum, south of Rome, and run them through electron microscopes, X-ray spectroscopy, and chemical mapping. What they found inside the concrete was something that had been visible to the naked eye for centuries and dismissed for centuries. Small, white, calcium-rich chunks, a few millimeters across, scattered throughout the mortar. Historians had assumed for 2,000 years that these were defects, lumps of unmixed lime that the Roman builders had failed to grind in properly. Sloppy work. Masic and his team showed that they were not defects at all. They were the active ingredient. They are called lime clasts. The hot mixing process gives them a brittle, nano-structured internal architecture full of reactive calcium. For most of the concrete's life, those clasts sit there doing nothing. The structure holds. But the moment a crack forms in the concrete around them, two things happen at once. Water seeps into the crack. The water reaches a nearby lime clast. The clast dissolves into a calcium-saturated solution. That solution flows along the crack, and when it meets the volcanic ash mixed throughout the rest of the concrete, it recrystallizes into new silicate hydrate, calcium silicate hydrate. Remember that compound. It is the molecular glue that holds all concrete together, ancient or modern, and it is the entire key to this story. The crack heals inside the material itself, using the concrete's own embedded calcium and the moisture that should have destroyed it. The Romans built a material that uses its own decay as fuel. Seawater feeds the structure instead of eroding it. The harbor concrete at Caesarea Maritima, 2,000 years under the Mediterranean, has grown rarer crystals over the centuries that interlock and reinforce the matrix from within. A team at the University of Utah, after a decade of studying these samples, called Roman concrete arguably the most durable construction material in human history. In 2023, the MIT team did one more thing that closed the case. They mixed up a batch of modern cement using the hot mixing technique with lime clasts deliberately included. They cracked the samples on purpose. They left them sitting in water for 2 weeks. The cracks closed. The Romans did not have a secret recipe. They had a technique, and the technique can be reproduced. Which brings us, finally, to your driveway. Because the same calcium silicate hydrate that heals Roman concrete in slow motion across centuries is the same calcium silicate hydrate that forms instantly when you spray one specific cheap industrial liquid onto modern concrete. And modern concrete contains exactly the leftover calcium that liquid needs to react with. The chemistry is sitting there in your slab, waiting. If you are getting useful information out of this, hit subscribe. The next half of this video is the part that affects your wallet directly. What the two compounds are, what they really do, what they do not do, and how to use them without paying 10 times the price for the same molecule at the hardware store. 6 years apart, in 2 different countries, 2 men accidentally laid the foundation for everything modern concrete maintenance relies on. In 1818, in Munich, a mineralogist named Johann Nepomuk von Fuchs fused soda ash with silica sand and dissolved the result in water. He got a thick, syrupy liquid that dried into a hard, glassy film. He called it Wasserglas, German for water glass. Today, we call it sodium silicate. It was the first deliberate, large-scale synthesis of the compound in history. Sailors and glassmakers had been stumbling onto crude versions of it for centuries, but von Fuchs made it on purpose, reproducibly, in volume. 6 years later, in 1824, in Leeds, England, a bricklayer named Joseph Aspdin filed British patent number 5022 for, quote, an improvement in the mode of producing an artificial stone. He had been heating limestone and clay together in a kiln behind his house, grinding the result into a fine powder and mixing it with water. When the mixture dried, it set into something as hard as the famous Portland stone quarried on the English coast. Aspdin named his invention after that stone. Portland cement. Aspdin's invention is today the most used manufactured material on Earth after water itself. Roughly 4.4 billion tons of Portland cement is produced every single year. Concrete made from it is the second most consumed substance on the planet, again after water. These are the two compounds. Portland cement, in any orange bag at any hardware store, between $5 and $10. And sodium silicate, sold by the gallon in industrial chemical catalogs for a few dollars per quart, and at much higher markups in smaller bottles, labeled as concrete densifier. Here is what happens when you apply them to existing concrete. Concrete is not solid. Under a microscope, cured concrete looks more like a stiff sponge than a stone. Microscopic pores, capillaries, and small voids riddle the matrix, mostly created by water evaporating during the original curing process. Water gets into those pores from the surface. In cold climates, that water freezes and expands, widening the pores into cracks. The cracks let in more water. The cycle accelerates every winter. Sitting around inside those same pores is a substance called calcium hydroxide. It is a natural byproduct of how cement cures. It can make up to 25% of hardened cement paste. It adds essentially no strength to the concrete. It is just there, inert, waiting to react with something. Sodium silicate is what reacts with it. When you dilute sodium silicate, 1 part to 4 parts clean water and spray it onto concrete, the liquid is pulled into the pores by capillary action. It is the same effect that pulls a drop of coffee up into a sugar cube. Once inside, the silicate meets the free calcium hydroxide already in the concrete, and they chemically combine. The product of that reaction is calcium silicate hydrate, the same molecular glue. Hard, dense, permanently bonded to the concrete at the molecular level. It fills the pores from inside the slab itself. Portland cement does something parallel for actual visible cracks. You mix it with clean water until it has the consistency of thick latex paint, brush it into a hairline crack and let it cure. As it sets, the same calcium silicate hydrate forms inside the crack, chemically bonded to the surrounding concrete. New concrete grown directly into old concrete. Multiple peer-reviewed studies have measured the effect. A study in the journal Construction and Building Materials documented significant gains in surface hardness from sodium silicate treatment and a reduction in concrete permeability of well over half. A separate study in Smart Materials and Structures showed that silicate-treated, micro-cracked concrete recovered its gas permeability and water sorptivity to values comparable with undamaged samples. That last detail matters. The chemistry does not just slow the damage. Within its limits, it restores some of the lost performance. And now the honest part of the conversation that the videos selling this technique usually skip past. This treatment is designed to do specific things, and within those things, it does excellent work. It densifies and hardens the surface layer of concrete. It dramatically reduces dusting, which is the fine white powder that comes off a bare concrete floor every time you walk on it or sweep. It seals hairline cracks and micro cracks. It cuts moisture migration up through basement slabs. It improves the surface against everyday foot traffic and chemical spotting. It is not a structural repair. It will not fix a crack that is currently moving. It will not fix a crack caused by foundation settlement because the underlying problem is still pulling your slab apart. It will not rebuild concrete that has spalled away or chipped off. It will not save a driveway whose subgrade has washed out underneath it. A sodium silicate treatment on structurally compromised concrete is a band-aid on a fracture. Anyone who tells you otherwise is selling you something or has not watched a freeze-thaw cycle destroy a slab. It also has limits the manufacturers do not put on the front of the bottle. Sodium silicate has relatively low chemical resistance compared to dedicated epoxy or polyurethane sealers. Oils, acids, and de-icing salts will still attack the surface, just more slowly than they would on untreated concrete. For outdoor concrete in harsh winter climates, you generally still want a top-coat sealer over the densification. So, if you see a video promising that $1 of sodium silicate will permanently strip every crack out of every concrete surface on Earth, you are watching a marketing message dressed in a lab coat. The real claim is more boring and more useful. For surface densification, dust-proofing, and hairline crack sealing on otherwise sound concrete, sodium silicate combined with Portland cement slurry is the best chemistry you can buy for the money. Which brings us to the price gap, and this part you have permission to be a little angry about. Sodium silicate, sold in raw industrial form by the gallon, runs about $3 to $8 per quart depending on supplier and concentration. 1 quart, diluted at the standard 1:4 ratio with water, treats roughly a 400 square foot garage floor. So the actual chemical cost to densify a typical home garage is under $1. That same chemical, marketed under a brand name as a concrete densifier, with a label that reads something like Advanced Silicate Densification Compound or Penetrating Mineral Hardening Technology, runs $30 to $140 per quart on the hardware store shelf. The chemistry is the same. Sodium silicate is listed right on the manufacturer's safety data sheet, sometimes under the chemical name, sometimes hidden behind a proprietary trade name. You can verify this yourself for free. Pull up the safety data sheet for any major brand of concrete densifier and read the composition section. The major chemical companies, Sika, BASF, Mapei, and Saint-Gobain, are all selling formulations built on the same base compound. The markup is paying for cleaner application instructions, sometimes useful proprietary additives, warranty coverage, retail shelf space, and a sales team. For a commercial contractor pouring a warehouse floor, that markup makes business sense. For a homeowner sealing a garage on a Saturday, paying 10 to 50 times the bulk price for the same active ingredient is paying for the label. Portland cement is the same story. A $6 bag of Portland cement contains enough material to fill hundreds of feet of hairline cracks. A tube of branded concrete crack filler costs $8 to $15 and treats about 12 linear feet. Same hydration reaction. Same calcium silicate hydrate bond. Wildly different receipt. This is not a conspiracy. It is just how information moves through a market. Cheap, durable, century-old industrial techniques do not run 30-second television spots. Patented branded products do. One more detail worth mentioning, because it tells you how seriously this chemistry is taken at the upper end of engineering. In 2011, after the magnitude 9 earthquake and tsunami damaged the Fukushima Daiichi nuclear plant in Japan, Tokyo Electric Power Company faced an ongoing emergency. Highly radioactive water was leaking from the damaged reactor buildings into the groundwater, and that groundwater was flowing toward the Pacific Ocean. They needed to seal the contaminated soil between the buildings and the sea, fast, in conditions where failure meant releasing radioactive water into the open ocean. Among the measures Tokyo Electric Power Company deployed was direct injection of sodium silicate into the contaminated soil. The compound flowed into the gaps between soil particles, reacted with naturally occurring calcium and other ions, and formed a gel that physically sealed the soil. It was documented in joint Japanese government and International Atomic Energy Agency reports between 2013 and 2015. It was not the only measure. Steel walls, frozen earth barriers, and active pumping were also deployed. But sodium silicate was part of the response at one of the most serious environmental crises of the 21st century. The same compound that hardens a residential garage floor was used because the chemistry does what it promises, predictably at scale. Step 1. Inspect the concrete honestly. If you have hairline cracks under about a 1/16 of an inch, surface dusting, a basement floor that feels chalky underfoot, or general sealing needs on otherwise sound concrete, this technique will help. If you have cracks wider than a credit card, cracks that are growing visibly year over year, areas where chunks of concrete have broken off, or any sign that the slab is moving, stop. Call a structural engineer or a concrete contractor. Sodium silicate will not fix structural problems, and using it on a moving slab will mask warning signs you want to be able to see. Step 2. Clean the surface. Power wash if possible. Wire brush any loose material out of the cracks. Compressed air for the dust. The treatment will not work through dirt or latents. Step 3. Mix Portland cement with clean water to the consistency of thick latex paint. Brush it into the crack. Press it in with a putty knife. Smooth it level with the surface. Let it begin to set for about an hour. Step 4. Mix sodium silicate 1 part to 3 or 4 parts clean water in a clean plastic bucket. Load a clean garden sprayer, the same kind you would use for weed killer, as long as you have rinsed it out thoroughly first. Spray the surface evenly, do not let it pool. You will see the concrete darken slightly as the liquid soaks in. Apply 2 coats with 30 to 60 minutes between them. Step 5. Let it cure. 2 to 4 hours of dry time before foot traffic. 24 hours before driving a car onto it. Some safety notes that get glossed over in more enthusiastic videos. Sodium silicate is alkaline. It can irritate skin and eyes. Wear gloves and eye protection. Keep it off glass, because once it dries on glass, it bonds permanently, and you will not get it off without abrasives. It will etch aluminum and vinyl, so tape those off. The compound is not particularly toxic, and there are food-grade versions of sodium silicate that have been used historically to preserve eggs. But the industrial-grade liquid you bought for your driveway is not the food-grade version. Treat it like a household chemical, not a beverage. The total cost for a full home garage floor and the visible hairline cracks running through it, somewhere between $10 and $20 of materials, depending on where you source the sodium silicate. Time. About 45 minutes of application plus drying time. The same molecular result that a professional concrete contractor charges $300 to $800 to deliver with a company truck, a fancier sprayer, and a proprietary product name. The Romans built concrete that lasted 20 centuries because they understood that calcium and silicate, in the right form, in the right place, will rebuild a structure from inside itself. The chemistry has been published since the time of Pliny the Elder. The modern version of it was figured out by a mineralogist in Munich and a bricklayer in Leeds, working on completely separate problems 6 years apart in the 1820s. It then sat in industrial trade catalogues for nearly 2 centuries and got rebranded for the consumer market a couple of decades ago, mostly for commercial flooring contractors. The homeowner version, where you can buy a quart of the raw chemistry and treat your garage floor for less than the cost of a pizza, never really got an advertising budget. Because there is no commercial incentive to teach you to buy bulk industrial chemicals instead of branded retail products with a $40 markup. That is not a conspiracy. It is just the way information moves through a market. Cheap, durable, century-old techniques do not run 30-second television spots. They get passed between contractors, then they get repackaged for retail, and the homeowner ends up paying for the packaging. If you have a sound concrete slab that dusts, hairlines, or just feels chalky underfoot, you now know more about the chemistry than most people standing in the hardware aisle. Buy a quart of sodium silicate from a chemical supplier. Buy a $6 bag of Portland cement. Spend an afternoon. Total cost, somewhere around $15 for a typical garage. Same molecule as the $80 bottle on the hardware store shelf. Same chemical reaction. Same result. 2,000 years ago in Rome, they did it with volcanic ash. Today, you do it with a garden sprayer. The chemistry has not changed. Only the marketing budget around it has. If this opened something for you, subscribe. I will see you in the next one.